So we're going to talk about Linux device driver. Many operating systems have device drivers. Linux, Windows, Mac OS. Today we'll focus on Linux as it's open source. It's widely used in desktop and also particularly embedded systems. We're going to talk about device driver, the big picture. We're going to talk about some examples, and we will compare polling and interrupt, and how do we implement those in the device driver. In the end of this part of the lecture, I will talk about our third lab, where we're going to design a device driver for our PIC-based sensor. Linux is an open source operating system. It's designed in a modular fashion. It can be extended in many ways, and in particular, device driver is one of the many ways to extend Linux to support many new emerging devices. Device driver is a piece of software, first of all, but it's kind of a special software that functions as black boxes which hide details of a piece of hardware. So a typical device driver is written for one class of devices. So you have device drivers for network interface cards, you have device drivers for webcams, and in our case, we want to have device driver for our embedded PIC sensor. Device drivers are designed to provide well-defined programming interfaces to others. And by programming interfaces, we refer to how you access this device in your program. For example, for let's say a webcam, and when you plug into a system, you will be able to access the system using a special device file. In Linux case, sometimes it's V2LD. For different devices, you may have different device files that associate with them. But some devices, they don't have a special file associated with them. For example, network interface card is a typical example. If you, in your Linux box, if you run ifconfig, that will show you the network interfaces that are attached to your Linux machine. You may see ETH0 or WLAN0 if it's a Wi-Fi interface card. These network interface cards, they do not have a special device file associated with them, but they have these device names associated with them. But either case, with device file or no device file, the other piece of software, user level software, can interact with these devices, hardware devices, using these well-defined interfaces. As Linux is designed in a modular fashion, and also in particular device drivers are very modular, so you can plug in them as needed. So when you have a new device, when you attach this device to your system, to your hardware system, what you need to do is to, in the Linux case, you do an insert mode, is that you insert the device driver to the module in order to be able to interact with the device. Even though your Linux kernel may not support that device at the beginning, you can, at runtime, insert a device driver module to the OS so that it will be able to interact with the new hardware. And device drivers are necessary for new hardware. If you design a new chip or new I/O device, that you typically need a device driver for it. And that's our case. We design a PIC sensor, which is not a typical, let's say, USB mouse or webcam that your OS may be able to recognize. For our case, the OS cannot recognize. And the way you interact with this hardware sensor is to use MB and LB if we do not have a device driver. Right? In the second lab, the way you interact with this PIC sensor is to use MB and LB to send the control signals, the control commands, and read the data back. So everything done is through those MB and LB. Now, for you, that's fine, because you design the whole thing from bottom up, right? You design the PIC sensor, you connect the wires, you know exactly what the control protocol is. So that's fine. But if you want to let other people to use your device, you do not want the other user to learn all these control protocols. You do not want them to be limited to the MB and LB methods. Instead, what you want to give them is a nicer interface. For example, what if you can provide them a file, and the name of this file could be /dev/parallel ADC, and the way to interact with your device is to read and write to the file, and the user of your sensor will be happy because he or she does not have to learn all the low-level details. But in order to provide such an interface, this special file, you need a device driver. Needless to say, writing a good device driver is art. There's a lot of things involved. First, you need to know how do you build a simple device driver, and on top of that, how do you optimize the performance? How do you debug? So all these things are really art that needs a lot of practice. The role of device driver. We say the device driver is a layer between application and the actual device. I just gave you an example, right? In order for a person to use your PIC sensor, you want to give the person a nice interface. You can give the person, for example, a file to interact with. One principle of writing a device driver is that a device driver is supposed to provide mechanism, not policy. Now, how do we understand this? Let's look at this example. By this time, I assume that you had experience with Linux. You at least use it. You can open a terminal. You can open a web browser, Firefox, to Google any things that you want to know. The way you interact is to use Windows Manager. Okay. You may use GNOME Windows Manager or KDE, different flavors of desktops. Let's use this as example to understand what we mean by the mechanism, what do we mean by the policy. Underneath the Windows Manager that you're using on the Linux box, we have so-called a X server. You can think about this as a device driver layer. This X server knows the hardware. It knows whether you have a onboard graphics card or you have a fancy NVIDIA multi-core graphics card. It knows the details of this hardware. Also, this layer, this X server layer, offers programming interface to user, and this user we actually refers to the designers of the top upper level Windows / session manager. At the Windows / session manager layer, this layer of software implements policy without the need of knowing about the hardware. So this upper layer piece of software does not really know about the underneath hardware. It does not know whether you have an NVIDIA graphics card or a built-in onboard graphics card. The X server layer implements the mechanism. For example, how do we push a pixel onto the screen? That's what the X server layer needs to become responsible for. But for the Windows Manager layer, the things it deals with is once you click this, how should I present the window, the size of the window, the color, etc. So that's the upper layer policy or style. So similarly, the device driver we're going to write is going to provide mechanism. To give you more detail, if we again use the special file as the example, if we want to have a special file to allow a user to interact with your PIC sensor, the device driver should provide basically 4 very basic functions: open, close, read, write. Okay? And it does not need to know about what you're going to write to the device or what you're going to read from the device. That's the concern of the users of that special file, the upper layer user program. The device driver only needs to handle these 4 operations, minimum. Okay? When you open the device, what should I do? When you close the device, what should I do? And when you read, what should I present to you? And when you write, where I should send these data to. So these are what we call mechanisms. Characteristics of device driver. This is we're talking about in general. It support both synchronous or asynchronous operations, and they can be opened multiple times because we may have multiple devices that belong to the same category. And the device driver will exploit hardware capabilities, and that's its own job. And it should not provide any policy-related operations. And most importantly, we want to keep device driver simple because it's going to function as part of the operating system, the Linux kernel. You do not want it to be a very complex driver, which could have several adverse effects. First, performance, and second thing is debugging. Okay? When you have more complex driver, chances are you introduce more bugs. This is a view of Linux kernel. What we see here at the bottom, these are different hardware resources: CPU, memory, disk, console, network interfaces. And this here, between these 2 dashed lines, these are what's inside the Linux kernel. We have different part of the kernel. For example, architecture-dependent code. This mostly deal with different CPUs because this Linux may run on an Intel processor, it may run an ARM-based processor or a MIPS-based processor. Memory management mainly deal with how do we allocate virtual memory and how do we map virtual memory to physical memory, how do we manage the page tables, etc. And the file system and block devices, these are dealing with the storage. Character device this set of module all designed to deal with devices that support classical interface, for example, serial interface or I2C interface, etc. And then we have one piece of this network subsystem, which is on top of this interface drivers. And these interface drivers talk directly with network interface cards. In a little bit higher layer, we have process management. This is going to be very critical to support multitasking, also the memory management, and also the file system, device control, and networking. The way to interact with OS is through this system call. For example, in your user application, you can do open. This is a system call. And in fact, we will see when we look at the template code we gave you, we do have an open function in the device driver. And when you open the special file from the user space, the user application actually gonna trap into the OS kernel, and which will invoke the open function of your device driver code. There are different classes of device drivers. Character device. These are designed to access a stream of bytes, and we should have minimal these functions: open, close, read, and write. There are many device drivers that belong to this category. For example, console or TTY S0. If you use the serial port in the second lab, particularly if you use USB adapters and the TTY USB 0, that's another character device. There are also block devices which can transfer data in units of blocks, and we have network devices and also USB devices. Device drivers are designed, loaded, and unloaded as kernel modules. So sometimes we refer to the same thing: device driver, kernel module. And as we explained earlier, that device drivers can be loaded at runtime. This is a big benefit to OS kernel designers. Because think about if you have to have a OS that can handle all different kinds of devices. That means you're gonna build a kernel that consists of the device drivers of all different kinds of hardware resources. You're gonna have a huge kernel. And that's a problem when you load the kernel, when you transfer the kernel, when you boot the kernel. So with this loadable kernel module, we can keep the OS kernel itself simple. And we later load the kernel modules as we need them. There are several things you need to do before you can develop a kernel module. You need to get the kernel source, you need to get the compilers, and also those could be different across distributions. So Fedora may be slightly different from Ubuntu or Debian or other flavors. In the next two slides, I'm going to show you very quickly a Hello World Linux kernel module or device driver. This particular kernel module is not associated with the real hardware, but the way to design, to compile, to load and unload is the same as we do for a real device driver for a real piece of hardware. So it looks like a C program, but it has some major differences. For example, it includes only the Linux kernel header files. Because this source code, once it's compiled, it's not going to be an executable that you can run directly on your machine. You're not supposed to do that. After you compile this code, it's going to generate, the compiler going to generate a .ko file. So for example, if we name this as a hello.c, it will generate hello.ko. And the way you execute it is by doing insert mode. So essentially you are pushing this .ko file down to the kernel to link with the kernel. You should not execute this .ko file or link this .ko file to your user space applications. There's some reserved macros or predefined macros where you can use to declare the license. This dual BSD and GPL license is essentially saying this code, this kernel module, can be used for either commercial or non-commercial cases. There are two functions here: hello init, hello exit. So it's not hard to guess that one of them is going to be executed when you load the module, and one of them, the other one, is going to be executed when you unload the module. So it's like a welcome and goodbye. Okay. So the init will be, this function will be executed when you load the module into the kernel. When you unload the module, this function will be executed. Right now, the actual operation is very simple. We just print a message. Now note that we're using printk. There's no printf in kernel. Printf is a C library. There's no C library in kernel. Kernel does not know about your printf or scanf, those functions. The way that you interact, especially when you want to print out messages, debug messages, is to use this printk. This current alert is the severity of this message. You can do critical, you can do info, you can do debug. Here we use alert. And then we return 0 to complete that function. For hello exit, it's a node type, so we don't have return. You can name these differently, but once you do that, you're gonna replace this hello init, hello exit for this module init and module exit. These two lines basically to tell the OS kernel that what is the welcome, what is the function. First function should be executed. So that's how we define that. And module exit, this is to say that when we unload this module, this function should be executed. You can rename these as you like. I mean, name of functions, not these. These are reserved macros by the kernel. So the way to compile is also very similar to develop a user level application. Once you have a proper makefile, you can just do make. I'll show you the exact makefile we're going to use. So when you do make, you're going to see something like this. So you enter these kernel source. It's going to compile this code, which is hello.c. So it generates hello.o. And they're going to do a mode post. And at the end, it's going to generate a hello.ko. This is the final outcome of the device driver code for Linux kernel module. You do want to generate a proper hello.ko or myDeviceDriver.ko. The next command you use, insert mode / that is to say the current directory hello.ko, which is the one you just generated. You have to do this using root privilege. On Ubuntu or Debian flavor Linux, you can do sudo. That's the same as you a real root user. So in the Ubuntu Linux machine, you do sudo space insert mode space / hello.ko. And depending where you run this command, okay, if you run it on the terminal, you may not see this immediately, but you can definitely see it in the system log if you do want to look at it. So this hello world, this, if you go back, this is hello world. This means that once you do insert mode, the init function is called. And in our case, we'll just print out this message. Because this module is very simple, we don't really use it for any real hardware, so we simply remove it after our testing. When you remove, you do rmmod, remove module. Again, if you use Ubuntu, you're going to do sudo space remove module hello. Now note that in this case, you do not use the suffix .ko anymore. And that's going to print the other message which we asked it to do in this hello exit function. Yes?
Why don't we use the .ko?
This remove module actually going to use the name of the module. There's one command which I can show you later. You can do ls mod, list module. So that will print out the kernel modules that currently inserted to the kernel at this time. So you will see, in this case, hello. This is the name of the module loaded to the OS kernel. This .ko, this just referred to that actual file. I was planning to let you do the practice, but for the sake of time, I will do this demo altogether at the very end. In fact, we're going to use a slightly different example, but it's very similar. Now we want to compare the kernel module with regular user applications. Kernel module needs to do init and exit very carefully. In the hello world example, we didn't do anything special. We just print messages. But when you design your device driver, you're going to do a lot more than that. You have to, for example, allocate a space, some memory space, as a buffer to store your data. And in that case, you have to remember to free this allocated memory when you exit. Just like you do in your user application. You do malloc and you do free, right? You have to do these pair carefully, otherwise you're going to have memory leak. For a user application, if you do not do that properly, chances are your user application will cause a segmentation fault. You just exit, which is not good, but not the worst. But when you design kernel modules, everything you do is on behalf of the kernel, behalf of the OS. If you access a non-pointer inside your Linux device driver, inside Linux kernel module, you're going to cause a very bad thing, which is called kernel panic. It's far worse than the segmentation fault of your user application, because the kernel itself, the integrity of the kernel is damaged. The operation of the kernel in the future is going to be unknown. So the kernel may cause inconsistent state itself, and it may cause many serious troubles. So you have to be very careful when you design your init and exit functions. In fact, everywhere in your kernel driver, device driver, Linux kernel module, you have to be careful, especially on the space allocation, memory space allocation. We talked about this briefly. There's no printf. The only thing you can do for printing is print k. You will need to include Linux kernel header files, nothing else. Anyway, just mention that bugs in device driver may cause crash. You will see in your log file there's a kernel panic, and you're going to see a lot of messages printed out with very scary addresses. So you have to be careful. And keep in mind that kernel module runs in kernel space, so whatever you do is on behalf of the kernel. That means you have full access to all the resources. And it has much greater concurrency in kernel modules than regular user applications. You have to consider interrupt handler, timers. Also, in the modern OS case, you have to consider SMP support. As a result, when you design a device driver, you must have the device driver designed to be entrant, so you can re-enter the function multiple times. You should have concurrency in mind, and also you should avoid any risk conditions. For example, if you have a FIFO buffer maintaining your device driver, you have producers to the buffer, you have consumer to the buffer, and you may have multiple producers, multiple consumers, and you have to deal with how you move the pointers to track the available bytes in the buffer. That's going to be challenging. Okay, so in our third lab, we are essentially going to design a device driver for our PowerPort device. I will mention a little bit after we finish talking about the PowerPort. I will talk about, for those people who are using serial port, what kind of device drivers we're going to design. But let's begin with the PowerPort device driver. You can read the detailed specification on the course webpage. But to summarize, what we want to do in Lab 3 is to design a device driver for our PIC-based sensor. We will design a module named PP_ADC. And this module will support these operations: open, close, read and write. And this is a character device, by the way. And we will provide this device driver, and associated with this device driver, we will create a device file named /dev/pp_ADC0. Once you have this device driver properly designed and loaded, and after you create this special file in your file system, and we should allow the user application to send commands to the sensor by using this special file. So we should allow the user to send these commands to your sensor. Note that we have more commands than last time. But we're going to send these commands by writing to this special file. And for some of them, for example, if we say want to get data, we will read this file. So that's the overall picture. That's what we want to achieve in Lab 3. Okay, so I'm gonna switch to let's switch to a demo. I want to show you how do you obtain the template code we gave you, and I want to show you also the steps to compile the kernel modules and how are you supposed to do the testing. So here I'm using a Linux box. You may have different flavors. This is a virtual machine, but on your desktop or your laptop you may have a native Linux, the commands are the same or similar. I put the source code on GitHub. For those of you who are not very familiar with GitHub, GitHub is a website that you can create repositories, and you can manage your code using version control, and specifically the git command. You can Google Git to know more about this command, but for our case, you only need to have one command to basically get the code. I will later send a note on Piazza to help you with these commands. So this command basically gonna get a source code package from GitHub, where I set up a repository under my username Lowell-UML/micro2. Micro2 is the repository name. So now I have that. So now I have a micro2 directory in my folder. And you actually see two folders under that. Lab 2 is the IO tutorial code, and Lab 3 is the one you want to look at. So first, when you look at the files in this directory, you see two .c files and one .h file. And you see some shell scripts, install, uninstall, and you see a make file, and you see a gem make. Okay, let me start with this make file. This make file is the one we produced for you to do the compilation of the Linux kernel modules. If you are running a Linux kernel 3.0 and above, you should be able to just do make to compile the kernel. There's a gem make. This is a script that you can use to generate a make file on earlier kernels, for example 2.6, 2.8 kernels. So typically,
Will you be able to get to that command line location like you just did?
you mean this location?
Yeah.
Yes, this is a public repository. Everyone has read access, so you don't need any user password to access this repository. So as long as you have a Git tool installed on your Linux box, you can get this repository. So I show you that we have a gem make script, which is longer than the make file. You may or may not use it or need it. I have this pp.adc.c. This is a template code that we provide, and on top of which you can implement your functions to communicate with your Oh, yeah, please switch off the light. Okay, sorry about that. I hope now you can see better. Before I go into every single line, I just want to show you another file we have. We have a characterdevice.c, okay, which is another open source code that you can get online and just put it together in this repository. For those people who did serial port in lab 2, you will need to use this file. Chances are you will need this file. You may have other implementations, but this is a good starting point. For those of you who did parallel port, you do not need to look at this character device.c. Okay, just a clarification on that. We already have a make file in this directory. If I do make, there are some warning messages from the compilation of ppadc.c. We can just ignore those. What you see here is we created character.ko and ppadc.ko. So these KO files are what we want, and these are the kernel modules. Since I'm using a virtual machine, I do not really have a parallel port, and I don't have a PIC sensor here. So I'm going to show you how we do the insert mode for the character device. If I do that, I can do a lsmod, which is to show the current loaded kernel modules. And I use less to see that clearly. So we can see that there are many kernel modules currently loaded, and many of them we don't really know what they are. Okay. If I do a grep character dev, that means currently we do not have this character device module loaded. And in the character device.c, this is the character device device driver example. The name of the device is character device, and I have a few operations for that device. Oh, by the way, we have this init and exit, and we have to have those. And beside that, we have this open, release, read, write functions, and we have these file operations associated with these functions. And we hard-coded a major number and a minor number. And major number and minor number are numbers you're going to need when you create the special device file, which I'll show you later. So let's take a quick look at the device init. This is the function will be called when you do the insert mode. This is essentially to register a character device, and I will print some messages. If there's an error or if it's successful, I will just print character device loaded. On the other hand, in the exit function, we'll just print character device unloaded. And we did something in the open function, because we record the number of times this device is opened, and we reset the pointers. And in the release function, we did the opposite. This is what we do in the read, and we do these in the write. Okay. For now, I'm going to just skip those details. So since we already did make, we already have these KO files created, so we can try to do a insert mode, basically to insert the module to the kernel. So I'll do a character dev.ko. Okay. Now you see nothing happened. Now you may wonder whether we loaded the device driver or not, because running this inside an X terminal, the kernel messages that we wanted to print out is not showing up here directly. However, it shows up in the kernel system log. The way you look at it, if you see the very end, this character device loaded. I can do the opposite. I just remove that kernel module. Oh, by the way, before I remove, I want to do a list all the modules I want to grab to see if indeed that module is loaded. So now you see this character device is in the list of the modules currently loaded to the kernel. Now I finished using this module, so I will remove that. And this time we use the name of this module, which is CHARDV. And I can check the log message again. You can see that this character device is unloaded. Okay, let me go back to this here. Alright, now we're going to spend a little bit of time to go through this ppadc.c to help you understand what we do in this kernel module. So as we noted here, that this is the parallel port sensor device driver. Yes.
Why is there a difference between the cloud and the SID? I mean, what's the basic difference in the way you build the driver for parallel and SID? Why is it different?
Okay, to answer your question, why they are different? Because the device is different.
No. But I mean, why isn't it the same format? I mean, just the way the device, I interact with the device is different, but it's different.
So that's one thing when you design the device drivers. Device drivers device drivers, first of all, they are designed for a particular device or class of devices. In Linux, different devices or different classes of devices, they are handled differently. For example, for this parallel port, you will see that we actually rely on the underneath parallel port APIs, layers, which is not necessary when you use a serial port. So that's one difference. Also, depending on whether you will use a character device to interact with it or not, you may or may not need to have the character device registration. The character device .c file we showed you as a part of this repository is just a template. Okay? In fact, there's a lot of things missing. I'll explain that later in more detail. Let's start with this parallel port. We declare the license as a GPL. You can add some descriptions. And this device name, this is the name going to show up when you do ls mod in the list of kernel modules. Now this first part, this ppadc structure, this is the structure that provides an abstract of the parallel port, where you will see some list. By the way, list is one kernel structure that can manage a class of devices. Also, we have this par device. This is the structure provided to the kernel, because as we see, the par port layer utilize this structure. Also, we have our own buffer to store the name. And claim is basically a counter to indicate whether this port currently has control of the port. The assumption is that there's only one parallel port in the computer. So you have to use some flag to prevent another one from acquiring the same port. Q counter is the counter to increment to record the number of interrupts arrived. This wait Q, I'm going to talk about that later. This is useful for doing waking up a sleeping process. So I'll defer the discussion 20 minutes later. Device number records the major number and the minor number of the device. We have two functions particularly designed for power port device. This is required by the power port layer. This essentially to allow this device driver to grab a power port and to reference to find that actual power port later when you trigger a open, write, read, or close operation. And these functions create, destroy are used to allocate that structure we just see or deallocate that structure. PP-ADC IRQ is the interrupt handler. Now we have these operations: open, write, read, close, and we have a poll. This one we'll talk about later together with the wait queue. You can ignore these for now. These are helper functions specifically for you to interpret the commands coming from the user space. And then we have the exit and init function. We will initialize a linked list. Now this PP-ADC FOPS, this is the main structure that will allow the linkage between your user level open function with the device driver level open function. Let me say it in a different way. When you call open on a file with a name, how does the OS know that this particular file is the one you are looking for? In our case, we want to provide a special file /dev/ppADC0 as my special file. You can have a user level application to say open by giving the file name. That open call will be trapped to OS. OS will have to know that what kind of device this is and what exactly the open function is designed for that device. This is the structure that provides this linkage. So from the user level open or read or write, you can trap into this device driver, this module, the actual open, read, and write function. Okay, just briefly, this is the init and the exit function. What we actually do is we register the parallel port. This is the PP driver, which is declared here. This actually provides the function pointer of this PP underscore attach and detach to this power port layer. Okay, I think you probably get lost at this point. what is the power port layer. You can just bear with me, forget about this, these two functions. Here, what you want to see, recognize this line. This is the malloc. Remember, at the beginning we have a big structure, okay? And that's the structure. So we need to have a memory buffer to store this big structure. So the way we allocate memory in kernel is to use kmalloc, and we can populate the fields to this structure. And then we initialize some of the items. For example, clear the counters. We also initialize this wait queue, and then we register this character device. So this device driver actually does two things at this step. First, it grabs or allocate the resource of the parallel port so that it can access the parallel port. The other thing is it creates a device, the character device, so that later you can use /dev/ppy ppadc0 to access it. So that there's two things it is doing right now. On the other hand, when you want to destroy this structure, you're gonna do the opposite. And keep in mind, you have to do the opposite sequence. Remember, when you create, you do kmalloc at first. So here you want to do kfree at the end, because you have a lot of register and deregister thing you need to pair up. Okay, let me forward several pages. Okay, this is the function I want to help you to understand currently. This is the open function. This function will be called when at the user application you do open /dev/ppadc0. This function will be called by the kernel, so it does several things. It searches for the actual device. It finds out the pointer to the structure. It tries to claim the port, and it tries to communicate with the device. Okay. Now here, this is something related to your PIC sensor. This ping, I assume you already did ping in the second lab. This ping, just doing this hello message, right? Ping and reply, ping and reply. Now you see here, I'm doing this for a couple of times. And ideally, your device should be alive. So this ping should return nicely. And that's exactly the things I'm checking here. If you are able to do the ping successfully to the device, I assume everything's all right. So I will just return 0. I'm done. Remember, this is in the open function. Okay? When you open that special file, when it gets down to the kernel, your actual device driver is checking with the real hardware. That's the main purpose of our open. If that's successful, that means this open is meaningful, so we should return success. Otherwise, I should clear up, right? I should release the parallel port I should print out a message, some message to indicate that this open is problematic because I wasn't able to do ping. So I will return this error code, this no def. This is a special error code in the kernel to indicate that there's no such good hardware. No, your PIC sensor is not working properly. Follow me? I think half of you are following, half of you are trying to follow. So, first of all, I think you want to understand why this function is called, or when this function is called. This hook open. This function is called by the kernel when your user application calls open in your user code, open that special file /dev/pp80c0. Once that happens, this hook open will be called by the kernel. And from the things you need to do with the parallel port, this is what we expect you to do to check the liveness of your actual hardware. And the way we check it is to send a ping message, which you already did in the second lab. And if your ping is successful, we'll just return normally. And to your user application, you will see the open call return nicely. So you return a file handler ID. Otherwise, this function will return an error message. To your user application, your open call will return -1. Okay? So that's the whole, from user down to the OS, down to this code, then return back to the user. For the close, it's very simple. Now read. Again, this hook read function will be called when your user application calls read. It's similar to the open function. It'll call from the user down to the kernel, down to this function. Now here, we left a space here where we expect you to read the actual value from the sensor. That's what you already did in the second lab in a different way, right? Using InB and OutB. And then the next thing you want to do after you read the value is to copy the value to a buffer which is supplied by the read. Now remember, if you do file operation as user application, when you do a read, you have to provide a buffer, right? Because when you do read, you expect to read something from a file. That's why you have to allocate the buffer before you call the read. And that buffer, that pointer, is going to be passed into this read function call. And that's actually this one. So the kernel will grab the value from the hardware, put it to this buffer, and then return. So that's why when this whole thing returns, your user application will get the actual content, the data, in the buffer you supplied. All right, let me switch to this special file. I keep saying this special file. Okay? You need a special file, and the way you create it is to use this command, make node-m is to provide the access privilege, name of the file, and this is the character device. Let me show it again. This is the character device. This is the major number and minor number. Now this number, this pair of numbers uniquely identify the actual kernel module or the device driver. So after you compile the sample code, when you do insert mode, it will print out two numbers. And the number could be different from the 255. So you need to change this to the proper number that printed out by the kernel, because it can allocate the number at runtime differently. Nice timing. So once you create this, then your user application can open, close, read, and write this file. And that's how the other four functions we just show you called subsequently. Okay, I think I have to stop here. I almost complete the explanation of the parallel port driver. I encourage you to get the code, start doing practice, just load the code to your Linux machine to see what happens. Next week I will keep talking about this device driver, and we're going to look at the polling and interrupt. For people who use serial port, I will send additional instructions on Piazza to help you to get started. Yes?
Major and minor are static values, so once, whatever your kernel assigns to that piece of hardware, it's always going to assign it.
For that session, before you reboot.
So you reboot and it could reassign.
It could be different.